In this illustration, we intend to simulate the masonry wall under the cyclic loading using simplified micro method in the Abaqus software. In this question, first the masonry wall undergoes a compressive load equal to 0.7 megapascal, and following that an in-plane cyclic loading will be applied to the masonry wall. After that, the hysteresis diagram of the masonry wall will be drawn. In this picture, the hysteresis diagram obtained from the Abaqus software has been compared with the results mentioned in the article. As you observe, the results obtained from the Abaqus software have a proper concordance with those mentioned in the article. In this picture, the deformation of the masonry wall undergoing a cyclic loading can be observed. Actually, we intend to simulate this article in the Abaqus software. The article is entitled Simulating Masonry Wall Behavior Using a Simplified Micromodel Approach. This article contains 3 sections. In the first section, the masonry wall under in-plane loading. In the second section, the masonry wall under out-of-plane loading. And finally, in the third section, the masonry wall undergoes an in-plane cyclic loading. In this training video, we only simulate the masonry wall under a cyclic loading in the Abaqus software, which has been pointed at in the third section. In this picture, you can observe the geometric shape of the masonry wall. The height of this wall is 1200 millimeters, and it has a width of the same 1200 millimeters as well. Here I intend to talk about different methods of simulating masonry wall in the Abaqus software. There are 3 methods of simulating the masonry wall in the Abaqus software: micro method, simplified micro method, and macro method. In micro method, geometric shapes of brick and mortar should be created in separated parts in the parts module. And following that, the properties of brick and mortar to be defined separately in the property module. Also, the properties of damage should be defined for the mortar. In simplified micro method, only the geometric shape of brick is defined in the part module, and there is no need geometric shape of mortar to be created. Therefore, the properties of mortar or the same interaction property between the bricks will be defined in the interaction module using the 2 cohesive behavior and damage options. In macro method, geometric shapes of brick and mortar will be created in form of an integrated and continuous part, and the properties of the masonry wall will constitute a combination of properties of both mortar and brick. The simplified micro and macro methods are mostly used to simulate the masonry wall, and the micro method is less commonly used. Simulating of these of these three methods, the macro method is the simplest method for simulating a masonry wall. I will click on mechanical menu, select elasticity and elastic. In this table, three quantities have been defined for Young modulus. The first quantity is for the brick, that is equal to 5,730 megapascal. The second quantity is for the mortar, that is equal to 565 megapascal. Actually, in micro method, Young modulus of the brick and mortar will be defined each separately, and you can use these quantities in micro method. The third quantity of Young modulus is equal to 2,888 megapascal, that is used in simplified micro method. In fact, this Young modulus is a combination of the brick and mortar Young modulus quantities, and one formula has been given for it in this article. Which can be observed here. Since we use simplified micro method in this question, we should use the quantity of 2,888 megapascal. The Poisson ratio is equal to 0.15. In this question, a Drucker-Prager model has been used for defining the properties of plastic. I will click on mechanical menu, then on plasticity and Drucker-Prager. Friction angle is equal to 36 degrees. Flow stress ratio is equal to 1. And dilation angle is equal to 11.3 degrees. Enter the geometric shape of half brick into the assembly section. Click on Create Interaction Property. select Contact and Continue. Here we should define an interaction property between the bricks. Actually, the properties entered here are the same properties of mortar, which cause the bricks to be stuck and connected together. First, I'll click on Mechanical menu, then select Tangential Behavior. From here, select Penalty. The coefficient of friction is equal to 0.75. Then I will click on Mechanical menu, then select Normal Behavior. In the next step, I'll click on Mechanical menu, then select Cohesive Behavior. Here, tick on Specify Stiffeners Coefficient option. Here the quantities of KNN, KSS, and KTT should be defined. KNN stands for stiffness of mortar in normal direction. KSS stands for stiffness of mortar in the first shear direction, and KTT is stiffness of mortar in the second shear direction. KNN is equal to 63 Newton per cubic millimeter. KSS is equal to 25 Newton per cubic millimeter, and KTT is equal to 25 Newton per cubic millimeter. I will enter KNN equal to 63 multiplied by 10 to the power of 9 Newton per cubic meter. KSS equal to 25 multiplied by 10 to the power of 9 Newton per cubic meter. And KTT equal to 25 multiplied by 10 to the power of 9 Newton per cubic meter. In the next step, I'll go to Step Module, click on Create a Step. This question will be done in 2 steps. In the first step, a compressive load will be applied to the top of the masonry wall. Also, in the first step, the weight of the masonry wall will be considered. In the second step, a cyclic loading will be applied to the top of the masonry wall. Here I select Dynamic Explicit and Continue. Time period is equal to 1 second, and the analysis will be done in nonlinear form, and OK. I'll click on Create. Select Dynamic Explicit and Continue. Time period is equal to 89 seconds, and OK. I will enter Load Module, click on Create Boundary Condition, then select Displacement Rotation and Continue. I'll select the bottom part of the brick wall. Done, and close all boundary conditions of displacement for it. In the next step, I'll click on Create Load, select Step 1. Here select Gravity and continue. I'll enter gravity of Earth equal to negative 9.81 meters per squared second. Click on this arrow, select the whole of the model, done, and OK. In the next step, I'll click on Create Load. Here select Pressure and continue. I'll select this surface, done. I will apply the pressure equal to 0.7 megapascal to the top of the masonry wall. In the next step, we intend to draw the hysteresis diagram of the masonry wall. Actually, we intend to draw this diagram in which the horizontal axis is horizontal displacement and vertical axis is called horizontal load. I'll click on Create XY Data. Here, select ODB Field Output and continue. Here I'll select Unique Nodal first, select Reaction Force directed at X, and then Displacement directed at X. Here I'll select this node that pertains to the place of cyclic loading. I'll click on Save and OK. I'll click on Create XY Data, select Operate on XY Data and continue. Here I'll select Combine. First I'll select U1 and then RF1 and click on Save As. Here you observe the hysteresis diagram of the masonry wall. I will transfer this diagram to the Excel software. The first column is displacement, the unit of which is meter. The second column is force, the unit of which is Newton. The diagram drawn here in red color is the one obtained from the Abaqus software. As you observe, the results gained from the Abaqus software are very close to those mentioned in the article, indicating that this question has been properly and correctly simulated in Abaqus software.